What's going on, everybody, and welcome to a neat video on the NEAT algorithm. So if you're not familiar with the NEAT algorithm, it stands for Neuroevolution of Augmenting Topologies, and as the name suggests, it's an evolutionary style algorithm. And the main crux of this is that rather than like in a traditional neural network, you've got a predefined, n layers, size per layer, and what gets tweaked through training is we're adjusting weights and biases. Whereas with the NEAT algorithm, what's happening is we're augmenting the topology. So we're actually changing the model itself. So as we're training, let's say this model, what we're actually doing is we're adding and removing things like nodes and connections. We can also change weights and biases, but that's not the main thing. Well, the main idea here is that we're actually changing the structure of the neural network. So we tend to start with a very simple neural network, and then it just kind of grows over time based on the structure that is most successful, i.e. the evolutionary aspect. If you want to learn more about how it works, I've pulled up a few things here. So first of all, we're going to be using the NEAT Python library to do this. And on this page, now I'm kind of lost. On this page, yes, here we go. We have the selected publications. Also, if you just Google the NEAT paper, you should find it. The original paper is actually pretty short, pretty simple, I think, to understand. Also of note, it was published in 2002. So this is kind of prior to major GPU advances, which also is one of the cool things about the NEAT algorithm is that you basically have to. It runs on the CPU rather than a GPU, so anybody can follow along. You're kind of limited at this point by your CPU power, but I will also say, at least through my own tinkering, there has been no problem that can be solved with the NEAT algorithm that is not solved pretty quickly. So you're not going to be training for days or weeks here. This is not that... It's just not the same kind of style of problem is going to be solved by the NEAT algorithm that would otherwise be solved through what we now know as like reinforcement learning algorithms that leverage GPUs. So I don't think we'll ever see the NEAT algorithm defeating AlphaGo or writing papers, but what it can do is produce some pretty interesting results. So anyway, what we're going to leverage this on, and I also wanted to just say, if you do want to learn more about how the true inner workings, if you basically go to the NEAT Python page and then you can go to the selected publications, this one goes into quite a bit more detail, but there's a whole bunch of information here. So you can, if you want, you can get a lot more information on how things work here. So anyway, I will close, and then the environment that we're going to leverage this on, at least to start, is going to be the OpenAI environments, purely because they are so simple to get started. And then we're going to change the environment just so you have an idea of when you change your environment, what needs to be changed in your kind of configuration file. So that's what we're going to be doing. So to get both of those, you're going to do a pip install gem. That gives you the basic version of OpenAI's gem. And then pip install NEAT Python. Hopefully everyone is on Python 3 at this point. Now, for the gem stuff, it's going to vary depending on different operating systems. This pip install gem should let everyone use at least cart pull, like these things. You should be able to do everything on this page with a simple pip install gem. It's when you want to use other things. So the other one that we're going to do is this box 2D walker. I'm going to do that. On Ubuntu, this is what I needed to install first before doing this. I fail on something, whatever the replacement for FFM MPEG is. I forget what it was, but I just needed to swap it for MPEG and it worked. So anyway, it's going to vary by your operating system, and you don't even have to when I show you what we do to change things, you can apply this to any other environment or make your own environment, and at the end I will show you the thing that I ended up doing, which is kind of cool. So that's the information. If you have problems or whatever, feel free to post it below and I'll do my best to help you, but like I said, it varies by operating system, and closed AI doesn't really help anymore. Okay. So the first thing I'll do is show you the cart pull environment. So in this case, we're going to use cart pull. The essentially, if you want to get the first observation, you just do an env.reset. That also resets the environment. The observation is just going to be a vector of values. In our case, it could also be, I think, a matrix of values, but in the case of cart pull, it is a vector. And we do print them out here, so I'll explain those in a second. Then basically we loop the environment. So while it's not done, just keep going, give us the reward, let us know if the environment is done for whatever reason. I believe with cart pull, the limit is 200 frames, and the reward is, I believe, each frame that you stay alive. So the idea of cart pull is to keep this pull balanced on the cart. So you have to move the cart to keep the pull balanced. So then let's see, the observation. This is going to be that vector we talked about. So this is any environment information that you have. So this is going to, in theory, be the input to the neural network. And we want the output to be whatever action that we want to take. Now again, the documentation on these environments isn't the greatest. So with cart pull, for example, sometimes it tells you, yeah, so at least in this case, we know we want to apply a force in the range of +1, actually not even in the range. It's either a +1 or a -1. And that just moves the cart left or right. Then we have, yeah, so in this case, the reward is +1, but it's not actually telling us what the observation is. So in this case, well, one, it doesn't really matter, but I will explain it in a second. So let's go ahead and, actually I want to run this from in here. And we'll just say Python 3, I think 3.8, env testing. Okay, so in this case, we have, this is our observation, that initial observation that we made, right? So I print the observation, and then we also print the action space. So that's what that discrete value is. Give me the... okay, so this is the observation. I believe it's something like cart, maybe cart position, cart velocity, pull angle, I think, and then like pull velocity from the tip. I think that's what those values are. But again, it's not really that important. They're just useful values. so that's the environment. I'm pretty sure that's what those are. But yeah, and then the action space. This just lets us know, like, hey, what are the options here? It's a discrete, so it's going to be either -1 or +1. That tells us that. And in fact, actually, this just says 1 and 0. So. Well, this says V1. Maybe that's the difference. I'm curious. Let's find out. Let's see if V1 is actually different. Let's try that one more time. It doesn't look like it. So just to put this, so you understand what we're looking at, zeros and ones, as we run this observation, we're just taking, so with OpenAI, you can just say env.actionspace.sample and get like a sample action. So it's just in effect, we're just doing random actions. So clearly, actually, the action is a 0 or a 1. Okay, sure. Okay, so yeah, so that is the environment that we're going to be using. Now, coming back over here, what we're going to do first is go back to Neat Python. We'll go to the GitHub page, and we are going to apply this we'll go to their examples. They do have a cart pull example, I want to say, single pull balancing. Hello. And yeah, they actually have a bunch of different, so they've written their own version of cart pull, good for them. But we're going to use the OpenAI one just for simplicity, so when we go to change the environment, it's more clear what changes. So there's two things. We have the evolve, so we're going to use the feed forward version of evolve. And then we also need the configuration file, so we're going to say config feed forward. So we'll come over here, and I think what I'm going to do is just copy and paste this entire thing. We don't need to import the print function from the future because we're using Python 3. Now, let's see. I am not going to import visualize. I'm not going to you can check that out later. That basically just visualizes your model. So I'm going to also delete that. And I'm actually going to delete that. Cool. Yes. Okay. So so here's the thing that, like, this is why I kind of wish there needs to be like some sort of API, because like all of this code is not going to change. It's really arguably this is never going to change. This is never going to change. Now, I could be wrong, but in all of the things that I use the neat algorithm for to play with it, I never changed any of this code to train. And then arguably the eval genome, this is the thing that you're going to change. This is where you are going to be running your actual environment, getting rewards, and notifying the this algorithm how good the simulation went. So this will change, but even this could be much better. I'm highly tempted to make something that sits on top of this package. But anyway, let's go ahead and basically add our environment. So again, their environment is essentially here. Yeah. So what we're going to say is, rather than sim, so actually I'm just going to kind of pop this over maybe here. What we're going to do is we need to import gym. We define our environment like so. Then runs per net. We don't need to have a bunch of runs per net. I'm going to say, I guess 2. This depends. This is going to depend on how does your environment start. Is it like a really random initialization? If it is, you might want to give the network a chance to have a statistically relevant number of runs before you kill it off, so to speak. So keep that in mind. We'll leave it at 2. That's totally fine. Simulation seconds is not relevant because this environment will kill itself on its own. So basically this here. So this, rather than this, becomes while not done. Fitness equals 0. We'll say done equals false here. The sim, this is where we're going to replace with the because we're multi, I think you'd want to put this in here because this is going to be sent out to many processes and you wouldn't want to share the environment. So yeah, so we'll throw in the environment there. While not done, this is where we I want to leave net activate. That becomes your action. Inputs. Okay, so there we go. So as we kind of butcher this, I just want to show like how to apply your own problem essentially. So while all we're trying to do is get the fitness. At the end of the day, we're saying, okay, for however many runs that we want to run, this network on, here's the environment. Here's our starting fitness. Let's actually run a trial here. And then we're going to append that fitness, since we might have multiple runs, to overall fitness. And then we return min, mean, max, whatever you want. So in this case, they're suggesting we return the minimum. I'm going to say, actually, let's go with np.mean, so numpy.mean. So we'll go ahead and import numpy. Import numpy as np. Cool. So let's continue our copy and paste of our environment. So while not done, we're essentially here. What we're going to do is m.render. We don't want to render it. We'll do this. Observation. Oh, we need to grab that very first observation as well. Action input net.activate inputs. We'll say action. So rather than taking this random action, we'll take the action that the net so net activate is kind of like model.predict, let's say, if you're used to deep learning. And we need that very first, is it m.reset? Yeah, so we need that very first observation. So observation equals m.reset. We need to figure out what is our action that we're going to take. We're going to take some action based on some observation. We get that action, we take that action, boom, we've got a new observation, and we have a beautiful loop. We also have reward. So now what we're going to say is fitness. How do we want to do this? This is going to be per frame. Something tells me their fitness might be calculated differently. We're going to say fitnesses. in this case, fitness needs to be plus equals. So we've got fitness is. This is total for the each kind of run. And then we need to kind of, in this case, it's how many frames did we stay alive, essentially. But we'll pass reward. It could also just be plus equals 1. But we'll throw in the reward just to keep it in line with all the possible environments that we might run. So I think we're good. Now we just need the config file. So yeah, so while not done, action, fitness, and then fitness is, we append this overall fitness score to here, and then we return the mean. Again, we're only doing this in case we ran many runs. I can't remember with cart pull. I think cart pull might initialize in the center, but then the pull might be in a kind of random position. I forget. Okay, I think we're ready, other than we now need the config file. So the config file, again, is a thing that I think could be severely cleaned up. So here, config feed forward. Cool, beautiful. Let's go into here. And we already had the, I guess I just left it in here. So I'll explain it. Let's open it up. Okay, so in this case, we're saying, so fitness threshold, again, there's kind of two things here. So this is going to return the mean, but then each genome has a population that has like different traits, I guess. So in this case, this is all about this very specific run example. What is the fitness we want to return? And then in this case, this is for like the group, I think. So max, but I'm going to go with mean again. There's a case to be made for min as well. Not important. Again, this is one of those settings that, like, for me, I have not really found, like, again, either the problem gets solved pretty easily or it just simply doesn't. And maybe, again, it might be because I'm an idiot and I don't really know exactly how all this is working. So please do feel free to tinker. I'm just telling you what I have personally found thus far. So fitness threshold. So this is basically going to be like, okay, at what point, based on this, is it going to be, so if the average of that genome is 75 or above, hey, we're successful, we're done. And then all we'll do from that point is return basically who is the best. So, and then we'll dump that model, and then we can use that model. So in this case, we actually need to be 200. 200 is you stayed alive for 200 frames. It's a simple problem. We should be able to stay alive for 200 frames. So we will leave that. Now, I'm going to come back to this, but I just want to point out, like, basically this, all the way down, really, I think all of these, again, these are things that you have to have them here, but they don't actually need to be here. It should just be something you can tweak if you want, but this could be so much simpler. And in fact, you shouldn't even have a config file. I feel like this could be a function call, really simply. Yeah, anyway, but this is what we have. So num inputs, coming back here, these basically the things that you're going to need to tweak is going to be, depending on your environment, it's going to be fitness threshold, population size. This is essentially how many of these processes are going to run at the same time. So this is going to depend heavily on how many cores does your CPU have and how challenging and how heavy is your model. So cart pull, very lightweight model. So I could probably set this to, I don't know, 500 and be totally fine. If you're on like a little 2-core laptop, maybe don't do 500, maybe do 50 or 100, or, you know, figure out what your number is. But yeah, so cool. Got that. Okay, num inputs. So this is essentially our neural network. So what our num inputs would be is what is the shape of our observation. In our case, we're calling it observation. Well, remember that was 4 unique values. So our input is going to be 4. Number of hidden. Again, this is going to depend heavily on what kind of machine you're running on. I think cart pull could actually be solved. This is tough. I don't know if it could be solved. I'm going to keep this at 2 for now, and then if I remember to, we'll set it to 0 just to see. I think cart pull could be solved with 0 hidden layers. And then num outputs. So again, in our case, this outputs either a 0 or a 1 is what we want. And we can see here the activation function that's going to be used is clamped. You can also, you have a default, and then you can also have different ones. I believe they're just separated by space. They have a whole bunch of activation functions, so we can come back here. I guess I didn't. Neat. Okay, we'll just search it again. Neat Python. And let's do activation functions. Clamped might be new to some of you guys. Cool. Why is it all... I don't like that. Anyway, here's clamped. So clamped goes from -1 to +1. We could also do... I don't know, you could do hat in this case. It could be pretty simple. Rectified linear would be an option. So our number of out... it just kind of, it's up to you. So we could actually have one at the output, and then is it a 0 or a 1? Or we could have 2 and then run an argmax. So I'll put it at 2 and we can just run argmax on it. And we'll keep clamped. I actually find clamped works really well. Again, I've tinkered so much with his activation functions. I like clamped. Clamped seems to be really great. So I'm going to go ahead and save that, and we'll come back over here, and actually our action is going to be np.argmax of the observation. So again, the output is going to be 2 values. We're just going to say, hey, it's either a 0 or a 1, because again, those are action choices. Action 0, action 1. So that should work. So coming back over to our config file, some of the other things that you might really have an urge to tweak, as I did, was these bias min and max. I really felt like, hey, that should be -1 and 1. And same thing with the this range here in the 30s. And then I want to say weights are also, I don't see weights in here. Oh, here it is. Blind. I tried putting those to -1 to 1, and that didn't do better. So again, like, these are all really great defaults. I would just leave them. I would really just start with this and yeah, try that out. So okay, so let's go ahead and run it. Save that. This is neat. Okay, let's run it and see what kind of errors that we see. Python 3.8. This is neat.py. Invalid syntax. That was not one I expected today, but it is what it is. Okay, let's try again. No. Oh. So we're still trying to import the original cart pull, and we're not using that. We're using Gym. Wow, we haven't made it past the imports yet. Config feed forward. Oh, we called ours config. They call theirs config feed forward. So again, you might have different config file names. There we go. This will save it as winner feed forward. Let's go ahead and just call it winner. And anything else? How many more errors? This is interesting. We are hitting best fitness of 500. I thought the max was 200. Maybe are we doing cart pull V1 now? Maybe cart pull V1 can go to 500. But I'm also curious why... So we hit the fitness threshold, but we had 500. Oh, this is the average fitness. And did we say we want to... I think we did say that, didn't we? Fitness threshold was 200, and it was a mean. So, okay. Everything is working how it's supposed to work, and I'm just a dummy. Yeah, okay, interesting. Okay, so the average here was actually 163, and so yeah, it just took a while to work up to that. But by a while, as you can see, what I mean is like a minute. So cool. Okay, so now it works, we think. We got a good score. How do we use it? So again, I find the application of these things to be challenging, but and this could also be very way simplified in my opinion. Oh, I've got it up already. So test neat. So again, this will never change. This is always going to be the same. You need to load in the genome. This, not going to change. The only thing that might change is the name of the file, but we already changed it to config again. This doesn't change. If it's not a feed forward network, that might change. But my point is, This is all like boilerplate code that we keep having to repeat, and it's kind of silly. We are not using cartpole v0, we're using cartpole v1, and I think that actually is important because I'm pretty sure cartpole v0 maxes out at 200, or maybe 200 is the solved state. I don't know. Okay, so we make our observation. While not done, what action do we want to take? I'm not sure what this comment is for. I have no idea. I'm going to get rid of it. Maybe it's for a different, I don't know. Oh, I think it's maybe for the bipedal. No, I don't know. Anyway, I'm going to get rid of it. In this case, we want it to be np.argmax of net activate observation. And then we step, and then we render. So let's go ahead and test it. Again, I'll put links to all this that way, because again, there's like no reason to write this out. Like, it's always going to be the same. But okay. So Python 3.8 test neat. Okay, as we can see, we are balancing the heck out of that pole. Okay, looks good. No surprise there. It must be 500 frames is the max because we were still very successfully balancing this pole. That's a darn good pole balancer. So if you wanted to do this with like reinforcement learning, it would take you longer. Like traditional deep reinforcement learning, it would take you much longer than like 30 seconds or whatever it took for us to solve this problem. So that's one of the cool things is it's such a lightweight and relatively intelligent way to like search for the, I don't know, the answer to a problem. Now, the problem with the NEAT algorithm is you're really only going to solve simpler types of tasks. So again, it's tasks like I could solve it with NEAT much quicker than I could write a program to do it, but I could write a program to also balance the pole, right? But I can use NEAT to do it much quicker, and it does a good job of it. So so now let's go ahead and let's apply this to that bipedal walker. So again, coming over to closed AI here, we're going to go to environments, and we're going to do this bipedal walker. Oh, this one he has to walk over stuff. We're going to keep it simple, but feel free, or maybe apply it to the lunar lander. Try something else. Well, I'm going to start with the bipedal walker. So coming back to, I guess I closed the other page. Here we go. Environment testing. Open up. Okay, so we're going to do bipedal walker v2. So I'm going to copy that name. I'm going to pasta that name. And again, this script doesn't need to change because we'll see what is our action space, what's our observation, and so on. So let's go ahead and run. Oh. Okay. So Python 3.8 env testing. Okay, so they've been so busy being open they haven't updated their website, I guess. So it's actually there is no V2 available. It is only V3. Oh, I have it. I had it the whole time already ready to go. Didn't have to make that mistake. I did this like a while ago. I've been sitting on the NEAT algorithm for a minute. Env testing. Boom. Okay, cool. Wow, that random was not that bad. Okay, let's go to tippity top here. Okay, so recall. This is our... What? I find this to be not useful. This is box. What is a box? I don't know what that means, but anyway, whatever. So this is our observation. This is I guess it's a matrix, but we'll flatten it out. It doesn't have to be. So Actually, it's not. It is just a vector. It's just properly formatted. Anyway, we've got what? 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. So 24 values. So our input is going to be a 24. And then down here, we've got, these are each of the sample actions. So I guess based on this, I can imagine a possible action is anything from -1 to +1. And we have 4 of them. Okay, great. So, again, coming back to here, let's check clamped again and just, I'm pretty sure clamped is -1 to +1. It is. So, boom, we can use clamped again. You can feel free to use some sort of sigmoid-y type thing or any of these other ones that you want. Just make sure it can actually do the range, right? So in this case, if you started with sigmoid, you'd have a problem, right? Because you would never activate to the negative that we need. So just keep that in mind. But you can use, imagine sine. What a crazy activation function. But you can use it if you want. Okay, so so we have our bipedal walker. What needs to change? We know input is 24 values, and we know, I think that's what our config file was actually left at. So we know, where are we? Input values is going to be 24. Hidden, we can keep it at 2. I forgot to run 0 hidden. Someone, just do it if you're curious, I guess. And then num outputs is going to be 4. So we'll go ahead and save that. And that's all we're going to change. We're not going to change anything else because we don't have to. Because you would have to think about, is clamped still a viable choice? But in our case, we want a range between -1 and 1. So cool, that's fine. So coming back over here, rather than cart pull v1, we're going to change the environment to be a bipedal walker. So this is our main kind of train script. Boom. Runs per net. Again, I'll just leave it at 2. I don't really care. Forget. I think in this case, I think reward is how far you got. Or is given for moving forward. If the robot falls, it's a -100. So I think, again, reward will be cumulative. So we'll just continue pulling reward. That might, like, these are the things that are going to change, right? Like how reward is calculated might change. Like you might actually only have a reward at the very end. So for example, I don't know, imagine you have, here, mountain car is a good one. You only get a reward if you make it to the flag. So anything else that you do doesn't give you a reward. And, simply moving back and forth is no good. So number of frames alive is irrelevant. So different environments will have different rewards. So anyway, just keep that in mind. But in this case, I think they stack just fine. Now, rather than doing an np.argmax on the output, actually, we're going to take our action based exactly on the output, right? Because the output ranges. Cool. So again, we'll do mean. That's totally fine. And then again, I'll just remind you that fitness criterion is mean. 200 might be a little much. We'll set that to max, and then because I don't want to wait for a mean of 200. I don't think we're gonna get there. But you've seen what a random is, right? Like we've shown random, and so essentially random is this, right? This is a random. So you'll know if we've learned something. I think we'll start at 50. I think we're gonna make it 50. And then we'll see how that works. So, cool. Whoops. Oh, now I gotta get this all back. Good enough. Okay, so let's go ahead and run that. So, Python 3.8. This is neat. I'm not sure what we're seeing all these for. What is this? Why? I'm not sure. Why? Maybe it's the input, because we're taking an action based on box bound casting to float 32. So I wonder what the output is that we're getting. Okay, so this is actually taking considerably longer. Let us... I think our population... Yeah. Our population might be a little large for this one. That's something I would probably tinker more with to kind of determine, like, is there any reason to have a population that large for... I think I might shrink the population just so we can iterate a little quicker. What was our pops? Whew. Okay, we'll set this to 250. Come back over here. How are we doing at this? Oh wait, did we finish? I don't know if this is the right one. We only have 2 things open. Best fitness. Best fitness was 85. Okay, so this should work actually. Okay, great. So let's come back to test neat now. Again, the only thing that changes here is, okay, what is the environment we're going to run? So we're going to run bipedal walker. And then rather than, an np.argmax, again, we're just going to run the straight output. Cool. All right, let's see how our walker did. I didn't think we'd get a result anytime soon. Python 3.8 test neat.py. Okay. 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 I mean, he's making moves. And you saw random. This is better than random. It's pretty good. Oh no! Okay, again, I want to stress that the neat algorithm produces stuff like this, which is, it's neat. It's cool. You could write a rule-based algorithm that does this and solves these environments kind of like this. But the neat algorithm, I would argue, for sure solves that one way quicker than I could ever write anything for. I don't think the neat algorithm is going to solve, hugely complex problems, purely because of the way that it goes about solving them. It's not quite brute force, but man, it's really close to brute force, where if you have a big search space and the only thing that could possibly fit is a very complex thing, it's going to take you forever to find it. So, in that sense, I suppose you might eventually have a really complex problem and the neat algorithm could find the solution, but it would take much longer than something like, deep reinforcement learning could. So anyway, that's pretty cool. So I encourage you to kind of tinker with the neat algorithm to come up with a unique application. You can use maybe the OpenAI environments or try something out, maybe, I don't know, tic-tac-toe or something like that, and see what you can come up with. It is truly a neat algorithm. I enjoyed kind of tinkering with it. So the environment that I wanted to try the neat algorithm on was Conway's Game of Life. If you're not familiar, it's an extremely simple game with essentially 4 rules that dictate cells spawning or dying. Some versions of the game have more or less rules, but it's very simple. You can look it up if you want, and you can even write your own game of life if you find this interesting. There's no actual movement, but the result of these births, deaths, and stagnations produce visuals and structures that do appear to move. What you see here is a random game with 2, and by random I mean initialized randomly, with 2 uniquely colored cells in a game of life that I wrote, but you could have just one color or you could even have many more colors. My curiosity was if the neat algorithm could actually learn to build structures that survive. So the way I did this was by allowing the neat algorithm to initially place up to 10 starting cells. Obviously this is a parameter that you could change. Then just see how many frames that this structure stayed alive. So if it ran off the screen, that was a death, and then also if everything just stopped, that was a death, and then also it was a calculation of repeating frames. So initially, the question was if any 2 frames, so in a range of basically 3 frames, is there any repetition? Because there's a lot of back and forth movement that winds up happening. So if you don't put any limitation on repeating frames, what you'll get almost immediately is this kind of 3-cell repetition, just flipping back and forth and back and forth and back and forth. So I knew going in there would be the flipping back and forth of cells, so that was something I thought of in advance and just knew would be a problem. What I did not expect was there is actually a sequence of 3 frames that will repeat over and over, and the algorithm actually relatively quickly learned this one instead. So then once I stopped that from happening, the algorithm was actually pretty quick at learning various structures, but it would always make the exact same structure, which kind of makes sense. So then I started randomly placing red cells as well, like in the same 10 by 10 window, just to see if we could come up with some different structures, and it did. So then I got curious, what if we let the algorithm place in a 10 by 10 window of a much larger map? What might happen in that case? So this was actually one of the first things that it made, was one of these little gliders. And then adding back in the kind of random red cells just to see what would happen. And then a much larger map, you can see here that actually just a handful of cells, in this case it was only 6 total cells, becomes what you see here, which is pretty cool. So it can place up to 10, but if it attempts to place a cell in the exact same location, then so be it. It just doesn't count. So I finally decided it'd be cool to make one large play area and let the neat algorithm place in essentially 4 quadrants of a largest map to start. I allowed to have also the same kind of random placement of the red cells, and then just see what happens. And this is the result. It seemed to be quite a fan of that starting placement U-shaped structure in this case. But there were other shapes, I promise, that it came up with. Like you saw the glider. There was another shape I called the 176er because it stayed alive for essentially 176 frames. Like I kept seeing that number and I was like, what's this? And there's this really specific structure that stayed alive for that long. So anyway, pretty cool. That's the neat algorithm with, I guess, a cool cherry on top by applying it to Conway's Game of Life. I encourage anyone interested to go ahead and tinker with the neat algorithm and come up with your own ideas. It's actually a really fun and, like I said, neat algorithm to play with, aptly named, and pun intended. So anyway, that's all for now. Questions, comments, concerns, whatever, feel free to leave them below. Otherwise, I will see you all in the next video.